Hello everyone. I know it's always difficult after lunch to have presentations, so I hope I'm going to give you not only energy, but green energy. So let's talk about carbon capture in the cement industry. So what are we talking about? Basically, cement is one of the largest emitter of CO2 in the industrial sector, with roughly 7% of the emissions, of the total emissions. It's sometimes hard to grasp what that means, but you can see if the cement industry were a nation, it would be the third highest CO2 emitter after China and the US. That may be another way to look at the dimension of the problem. But the problem is even worse for the cement industry when you look at this number here, 6.9, where this is the kilo of CO2 per revenue dollars. And you see that the cement industry has very little money to afford as extra cost to its production cost, with a very high ratio of CO2 per revenue dollars. And that's the other challenge, which means that the CO2 capture technologies for cement have to be cheap. So where are the productions taking place right now? Not surprisingly, you see China here. So on the left, you have 2014. On the right, you have 2050 prediction. So China has a huge construction boom and infrastructure boom in the last 20 to 30 years. And you see that it's going to decrease over the years, which makes sense. We can argue on the exact number, but the trend is correct. In the meantime, you have India, which is growing and reaching the level of China by 2050, as well as growth in Asia, like in Indonesia, and in Africa, where there is a lot of infrastructure required. You see also a growth in America, and we were talking at lunch with some of you of the IRA, the Inflation Reduction Act, and some other decisions taken by the government to boost infrastructure, which has been aging without a lot of investment. So that makes sense that there is an increase. And Europe is relatively flat, as forecasted. I think we have a lot of good infrastructure overall, for instance, compared to the US, because we have been reinvested in the infrastructure. And from a residential construction point of view, there is a lot of regulation now to build what you want, and also a consciousness that it's better to buy, for instance, a house which is made rather than building a new one to reduce your impact, which that's what I've done recently. And that's an example. So not surprising that it stays flat in Europe. So where is the CO2 emitted during the process of making cement? So I just here have a quick summary of the process, where you go from the quarry, you crush the raw materials, transport them to the cement plant, then you have the clinker and cement manufacturing process, the cooling, then you have a cement mill to make small powder, and then it is transported where it is required. And you can see here that this is at the kiln stage that you have the biggest emission of CO2. Two reasons. One is the fuel, the energy that you need to heat up the kiln, and the second is the CO2 emitted by the chemical reaction taking place in the kiln. And basically you have 40% on the right side, 40% of the CO2 which is coming from the energy you use, and 60% is coming from the chemical reaction happening. So how to reduce the greenhouse emission from the cement industry? Of course, as we heard earlier, the best way to reduce the CO2 emissions is to use less cement, and that can be done with reusing the concrete, to find substitute to concrete like timber, having more efficient buildings where you can use maybe less material. But all the studies which have been made shows that you can only reduce by max 30% the emissions from the cement industry. The other way is to work on the process itself of making cement. You can use more greener fuels like hydrogen. So you can basically replace the 40% of the thermal emissions. Obviously, you need to have somehow a green or at least blue hydrogen to make sense. You can use also bioenergy, and here the study says up to 40% because the concern is that there might not be enough biomass to produce the quantity required for the cement industry, which will compete with other usage of bioenergy. And so carbon capture is the best option for cement, where you can capture up to 90%, because not only you capture the emissions from the thermal side, but also from the chemical reaction side. And you can go up to 90%. You can go higher. It's a question of price and purity you want to reach. So what are the 5 key technologies that exist today in the market? There are quite a few others, but I focused on 5. The most well-known is the amine technology. But as we saw from Min's presentation earlier, this is quite expensive, and that's not workable for the cement industry. Already in practice, TRL 11, so it's valuable, but not economically viable for the cement industry. Then you have kind of the least developed, or the whole list, is the calcium loop, where you take the lime as solvent to capture the CO2 in one reactor, and then you use a second reactor to separate and go back to CO2 and CaO. This is, you need 2 reactors investment, so it's energy intensive, and typically you will need a new kiln, which is extra capital money. Oxy-fuel, which is another technology. Oh, here you have combustion of fuel using basically pure oxygen, and then you are left with water vapor and CO2, which are very easy to separate. But any change in your clinker formulation will have an impact on that technology, as well as the gas change. So it's very sensitive. Direct separation, here you strip the CO2 directly from the limestone. So as you don't mix with other combustion gases, you don't need so much energy for the process, but here again, it's quite sensitive to the clinker formulation. Then you have physical separation, and here you have 2 types. One is physical adsorption, where you use a solid surface to absorb the CO2 with an active carbon for instance, or metallic oxides or zeolite. Or you have a physical absorption, where you use a liquid to absorb the CO2. And once you have absorbed the CO2, the way you release it is either by temperature swing adsorption, pressure swing adsorption, or vacuum swing adsorption, or some combination. And this is a technology which is coming to market with pilots ongoing. As we discussed, one of the key challenges is the cost. And here you see some of the technologies I presented and the costs, which are around 80 to 100 mark that we saw also from Min this morning, which is very expensive for the cement industry. But there is a new technology, and I'm happy to be the chairman of this company, is NOADA, which is using this physical adsorption, so the 5th category, with VPSA technology to remove the CO2. And here we are reaching cost of 16 up to 30, depending on the flue gas composition, cost per ton of CO2 captured. So this is quite a game changer for the cement industry. So how does it work? So basically, you have a flue gas coming with the CO2. We cool it down. It goes for a column where we have the MOF technology. Then it comes out as pure. The first column gets filled with CO2. Then it is moving to the second column. And as the second column fills up, the first column is dissolving the CO2 and with vacuum, and then we get pure CO2. We have about 80% recovery rate and 95% purity of CO2. Basically, the technology is ultra energy efficient because it doesn't use heat. Only use some electricity for the chiller and some pump. It is very modular because basically it's coming in a container and it's kind of plug and play. And the more you need columns, the more you can add either columns in the container or potentially add more containers. Mature process in the sense that the technology is based on VPSA, which is quite well known in the industry. And the MOF technology is the core know-how of the company, which has developed that for the last 10 years, where they have a very high knowledge about different composition, shapes, size of the MOF required for a given type of flue gas. It's heatless, as I said, flexible in the sense that you can adapt to any kind of flue gas. The company has an in-house pilot to mimic the flue gas composition, so you can adapt and optimize the MOF that you use, and non-toxic solvent, because they use a very unique technology to produce the MOF, which is mechanochemistry, so which is quite an elegant way of producing reliable MOF. So going forward, what does it take for making carbon capture a reality? Because capturing carbon is good, but what do we do? Policy, regulation, and funding from government. So putting some emission trading system in place, for instance, regulating the CO2 market to have a certain level of pricing on CO2 will be fundamental. CO2 transportation and storage is also an integral part, and I should also mention usage. As I said, capturing the CO2 is one thing. What do you do with it? So there is a whole ecosystem which needs to be developed in parallel to capturing. And specifically for China, yes, there is new plants which can be more efficient in terms of CO2 emissions. But still, there is a lot of emissions due to the amount of cement which is produced. So there will be a need for some retrofit of the cement plants in China. The good news is that when you look at the storing capabilities, according to the studies, some 45% of the emissions of this power energy intensive, and cement is part of that, are within 50 kilometers of the potential CO2 storage places, which is making it economically viable because you don't have so much transport. And 65% of the emissions are within 100 kilometers. And that could represent 40 years of current emissions that can be captured. And also, last but not least, there is an emission trading scheme in place also in China, which is, I think, a key element to make carbon capture a success. So this is, in a nutshell, what I wanted to share with you about cement. To summarize, there is today technologies available at cost-effective way to capture CO2 in the cement industry, but the ecosystem around it needs to be built. And I was also always, I'm seeing Keith here, usage of CO2 is absolutely fundamental, and China can rely on econic also technology for using CO2. That's the key, but we are there in terms of carbon capture. Thank you for your attention.